So now that we know the definition of the sum of an infinite series, we're going to try to use it to calculate the sum of a particular series. So the example we'll do is determine the sum of the series 1 over n plus 1. So first of all, just to map this onto what we know, an is equal to 1 over n plus 1. This is the general term of the series. It's also the general term of an underlying sequence, but what we're interested in is finding the sum of this series. So what we're going to do is we're going to write out the sequence of partial sums and see if we can calculate the limit of that sequence of partial sums. Recall that the basic principle here is that the sum of the series, if it exists, is equal to the limit as n approaches infinity of the sequence of partial sums. So we need to actually write out the sequence of partial sums to see if we can calculate that limit. So let's write out, first of all, let's put this series in a little bit of a more convenient form, because I think it's going to make it easier to see what the sequence of partial sums is. So first of all, note that this expression 1 over n plus 1, if I had given this to you with x's, it should call to mind partial fractions. I'm not going to perform the partial fraction decomposition. Go back and see our lecture on section 8.6 if you want to see how that works. I'm simply going to give you the partial fraction decomposition. Oops, there we go. And write that is 1 over n plus 1 is equal to 1 over n minus 1 over n plus 1. If you actually do the partial fraction decomposition the way that we did in section 8.6, you will in fact get that as the decomposition. So what that means is that the sum from n equals 1 to infinity of 1 over n plus 1 is equal to the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. And you're going to see that this is a little bit easier to work with for the purpose of dealing with partial sums. So let's write out some partial sums. Let's write out S1 is just going to be the first term is going to be the sum of the first one term, in other words, the first term. So since we're using this expression for the general term of the series, because we determined it was equivalent to this general term, that's S1 is just going to be 1 over 1 minus 1 over 1 plus 1, which is 2. Let's write the second term. That's going to be, the second partial sum. So that's going to be the sum of the first two terms. So that's going to be 1 over 1 minus 1 over 2. That was the first term. Plus, now we're at 2, so that's 1 over 2 minus 1 over 3. So just to be clear on what I'm doing here, what I have is n equals 1. Here I have n equals 1 and n equals 2. Let's write it out for the third term. The third partial sum is going to be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And again, just to be clear, what I've written here is n equals 1, n equals 2, and n equals 3. And I'm just adding those up. Let's write out one more, because I think it'll become a little bit more apparent if I do this. So this is going to be S4. The fourth partial sum is 1 over 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth plus 1 fourth minus 1 fifth. Now look what we have here. What happens when you write out the terms this way is you see that here, if you look at S2, I have negative 1 half and positive 1 half that cancel each other out. So this entire expression just comes out to 1 over 1, which is 1 minus 1 third. For S3, I have negative 1 half and positive 1 half, and also negative 1 third and positive 1 third. So what I'm left with is 1 minus 1 fourth. And for S4, you can see the same thing. I cancel the positive and negative 1 half, positive and negative 1 third, positive and negative 1 fourth, and what I'm left with is 1 minus 1 fifth. So if S2 is equal to 1 minus 1 third, and S3 is equal to 1 minus 1 fourth, and S4 is equal to 1 minus 1 fifth, hopefully you can see that for any Sn, because of all these cancellations that I get in the middle, Sn is going to equal 1 minus 1 over n plus 1. So I now have an expression that gives me the nth term in the sequence of partial sums. Recall that the sum from n equals 1 to infinity of an is equal to the limit as n approaches infinity of Sn. So that's so what I have now is I have an expression for Sn. Let's see if we can calculate that limit. That's just going to be limit as n approaches infinity. That's capital N, 1 minus 1 over n plus 1. It should be fairly easy to see that this is just going to equal 1 minus 1 over infinity, which is 1 minus 0, or 1. So there we go. We've now used the definition of we've used the definition of the sum of an infinite series, using its definition as the limit of sequence of partial sums, to calculate the sum of this series. And it turns out that if you add up all of these terms in this series, which we showed was, well, we didn't show, but I told you through partial fractions, is equivalent to this series. It's just algebraically equivalent. If we add up all the terms in this series, we just get 1. So this is our first example where we're adding up an infinite number of terms we're adding up an infinite number of terms in a sequence. When we add them up, we call it a series. And even though there are an infinite number of them, we get a finite number, which in this case is 1. The series whose sum we found in this problem actually has a name. It's called a telescoping series. It's actually a fairly important series when you go on to higher level math such as analysis, because this is instrumental in, for example, the proof of the fundamental theorem of calculus. I don't want to go into the details of that right now, but the reason it's called telescoping series, I think, is because of the degree of overlap that you see. I think this is supposed to call to mind like one of those folding telescopes where the pieces sort of nest within each other, where they collapse into each other. I think that's what it's supposed to call to mind. I don't know if I'm drawing that type of telescope correctly, but that's what telescoping refers to. Anyway,